So in this video, what we're going to do is talk about what we call our row operators. And our row operators allow us to solve a matrix the same way we would a system using elimination. And there are three row operators that we can use in any matrix. The first one is the most basic, which allows us to switch rows whichever way we see fit. So we can always change the rows, and it's called a row switch within a matrix. The second one is basically multiplying any row by a number, just like you would when you try to eliminate and you try to get the variables to be the exact same. You can multiply any row by a number, which makes it a multiple of the equation. But it's the exact same equation, just the multiple of it. The third one, you can add rows to each other. So we can add rows, or in our case, we may want to subtract rows. Subtraction is the inverse of addition, so we can do that too. And so when we go through this, and here's what we're going to do. This first one gives you the exact method to actually solve this equation. Here's how we would solve a matrix using row operators. The first one says to switch row 1 and row 2. That's what your first operation is. So we're going to start by writing out we already have the augment. And in the augment, what I'm going to do is R1 and R2. So I'm going to switch R1 and R2. So right now, here is R1. Here's row 1. Here is row 2. I'm going to switch those rows first. So now I'm going to get 1, 2, 4, 2, -1, -7. The next one says to multiply -2R2. So when I do that, here's what I'm going to do. I'm not going to touch R1. I just want to multiply by -2R2. So when we do this, we get the first row, 1, 2, 4. Second row becomes this, -2R2. So -2 times 2, a -4. -2 times a -1, +2. A -2 times -7, +14. So that is the second step, which was -2R2. We write it like that. The last thing says to do -2R2 plus R1. So this one is going to show you how we add the rows. So again, we're not going to touch R1. So we have 1, 2, 4. But here we're going to go -2R2 plus R1. And remember, we just did -2R2. So now we're going to add it to R1. So here's what's going to happen. When I multiply, again, I'm going to show you the exact process. We're going to multiply -2 times R2. -2 times R2 is this right here. We just did that. And so we did that. We got this -4. Now it's telling me to add it to row 1. So on that new row, then, -4 plus 1 is a -3. -2R2 gave me this 2 right here. I'm going to add that. When I add that to the row, I get 4. And then again, -2 times that gave me this 14 right here. When I get this and I add it to the next row above it, I get 18. So this is how we use the row operators to make new rows and to solve. We're going to actually try to solve this by creating our own row operators. I'm going to actually give you the row operators. We're going to follow the row operators to solve an equation next. So what I've done here is I've given you the exact row operations you need to do to solve this matrix, right? To solve this system of equations. Generally speaking, we would solve the system by using elimination. And I'll show you how to do that real quick to remind you what we've done so far. If I want to solve 3x1 plus 4x2 equals 1 and x1 minus 2x2 equals 7, remember we would try to eliminate one of the variables. And here I'm going to eliminate the x2 variable because it has opposite signs. So to do that, what I would do is I would leave the top equation alone. So I leave 3x1 plus 4x2 alone equals 1. And I'd multiply this bottom equation by 2. And I'd get 2x1 minus 4x2 equal to 14. And remember, we're going to eliminate here. And then we're going to add these by like that. And we get 5x1 is equal to 15. Divide everything by 5. I get x1 equals 3. So I know x1 equals 3. I can go back and find x2 by doing 3 times x1 is 3 plus 4x2 is equal to 1. So I get 9 plus 4x2 is equal to 1. if I want to solve for x2, I'm going to subtract off 9 on both sides. I get 4x2 is equal to 8. Divide everything by 4. This is a negative 8. Divide everything by 4, I get x2 is equal to a negative 2. So I'm going to use this exact same process for the most part to solve using a matrix though. And in the end, I should get a solution of 3, negative 2. So doing this exact same process, but using matrices, here's how it works. The first thing I'm going to tell you to do is to switch row 1 and row 2. And I'll show you why we're doing that later. But for right now, we're just going to walk through these actual row operators. So I'm going to create the augmented matrix first for this. The augmented matrix looks like this. It's 3, 4, 1. Then you have 1, negative 2, and 7. And the first thing says switch row 1 and row 2. So when I do that, I get 1, negative 2, moves to the top, 7, 3, 4, and 1 moves to the bottom. My next thing says to multiply row 1 by negative 3 and then add it to row 2. And it's going to replace row 2. So what that means is I'm not going to touch row 1 at all. I'm replacing row 2. So the only one I'm going to touch is row 2. So my top row stays exactly the same. But my bottom row, I'm going to multiply everything in row 1 by 3. So for instance, 3 times 1 by negative 3. A negative 3 times 1 is a negative 3. And I'm going to add it to the second row. So negative 3 times 1 is a negative 3 plus 3. That makes this into a 0. And I'm going to do negative 3 times a negative 2 is a positive 6. Plus 4 is 10. And the last thing is negative 3 times 7 is a negative 21. Plus 1 is a negative 20. So looking at this new matrix then, what I want to do now is I'm telling you to multiply, or in this case, we're really dividing, but matrices you always multiply. And remember that multiplication is the opposite of division, just like division is the opposite of multiplication. So I really want to divide this row by 10. But to write that as multiplication, I'm going to say 1/10 times row 2 replaces row 2. So again, I'm not touching R1. I'm not touching row 1. So row 1 will still be 1, negative 2, 7. But R2, I'm going to divide it by 10. Well, 0 divided by anything is 0. 10 divided by 1/10 is just 1. And then negative 20 divided by 1/10 is negative 2. And remember what we learned from a generalized system and back substitution? Well, now I can see that the x2 variable here is equal to negative 2. I have an equation for x1, which is x1 minus 2x2, that's equal to 7. Well, x1 minus 2 times x2 is just negative 2. We just found that. That has to equal 7. So when I solve this, I get x1 plus 4 is equal to 7. Subtract out 4 on both sides, and I get x1 is equal to 3. And so my solution here is the solution 3, negative 2. And if you recall from what we did using elimination, we also got a solution of 3, negative 2. So this process works both ways. We're just shorthanding the actual math and all the stuff that we did over here in elimination. So let's look at one more. And again, we'll start off by writing the augmented matrix for this. So the augment consists of 2, negative 1, that equals negative 7. And then we have 1, 2, and 4. First step says row 1 and row 2 need to switch. So we're going to switch row 1 and row 2. So again, I'm going to get 1, 2, 4, 2, -1, -7. Next step says to multiply row 1 by 2 and then add it to row 2 and replace row 2. So again, I have not touched row 1. Row 1 is going to stay as 1, 2, 4. I'm replacing row 2 with something. So I'm going to multiply everything in row 1 by -2 first. So that'll be -2 times 1 is a -2 plus 2. That becomes a 0. -2 times 2 is a -4 plus 1 plus a -1 is a -5. -2 times 4 is a -8 plus a -7 is a -15. Then the third step says to divide or multiply by -1/5 or divide by -5. So row 2, and I'm not going to touch row 1 again. So row 1 is still 1, 2, 4. But row 2, dividing everything by -1/5, this is 0, that's 1, and this is 3. So now I see that x3, or x2 in this case, is equal to a +3. And to go back and find x1, I have an equation x1 plus 2x2 has to equal 4. Replacing x2 with the value of 3, because we know that x1 plus 2 times 3 has to equal 4, which means that x1 plus 2 times 3 is 6. That equals 4. I want to subtract 6 from both sides, and I get x1 equal to a -2. So my solution set is -2, +3. And again, remember, this is what we call a consistent and dependent solution. It's consistent and independent because we have a solution and it is a unique point. But we're using row operations, and we're going to get more detail on how to do these row operations to actually solve matrices in our next lesson.